So this video, we're going to be creating an interpreter for the brainf-ck language in x86 assembly. So the purpose of this is to show you both how to write an interpreter and how to code an assembly. So let's look at how brainf-ck works before we work on trying to interpret it. So the most important concept in brainf-ck is that memory is represented as a bunch of 1-byte cells forming like a big strip. The same as in a Turing machine. So brainf-ck is a very minimalist language. It's got only 8 commands, and the commands are plus increments the current memory cell, minus decrements it, period prints the current memory cell value, comma inputs into the current memory cell. These angle brackets move left and right in the memory strip, and the square brackets begin and end a while loop, which does a while loop while the current cell is not equal to 0. Any other character is a comment and it's just ignored. So some examples of brainf-ck code would be this one over here. We see 10 plus signs in a row followed by a period. So what that does is that it increments the current cell 10 times and then prints it. So if the cell were initialized to 0, which it is when the program starts, this would print a new line character because new line character is ASCII value 10. This one over here inputs a character and then prints it because comma inputs into the current cell and period prints the current cell. This one repeatedly inputs and prints until a 0 character is inputted. So here we input a character, and then while the current value is not equal to 0, we print the current value, and then input a new value. This one does the same thing, except it exits when a 10 is inputted, which is a new line. So input a value, decrement by 10, and then now we do the while loop so that so if the inputted character minus 10 is equal to 0, then we exit out. And then we plus by 10 to undo the minus we just did, print, input a new character, and then do the same thing where we decrement by 10. This program over here moves to the right until we hit a cell that has a 0 in it, because this angle bracket, the greater than sign, moves to the right in the memory, and the while loop repeatedly does something until current memory value is 0. This one moves the value in the current cell over to the next cell to the right, because let's say we're in cell 0. This bracket, I should just start calling it greater than sign. This greater than sign moves over 1 to the right, increments, then we move 1 back to the left, decrement. So we repeatedly increment the cell to the right and decrement the current cell until the current cell is equal to 0, which pretty much just amounts to moving the current value 1 to the right. This program, we're going to calculate 10 by 10, or 10 times 10, assuming that both cells are initialized to 0, which they are in the beginning of a program. So first we add 10, then we repeatedly move to the right, add 10, move to the left, decrement by 1. So this is going to happen 10 times where we increment the second cell 10 times. So we're going to do that 10 times 10 is 100. And then at the end, we move over to that cell. The reason that I'm showing you how to do that is because let's say you want to print the H character. What you would do then, increment the current cell up to 100, and then increment it 4 more times and print. So that gets to 104, and H is 104 in ASCII. If you wanted to print high, so this is going to be our simpler example of Hello World that we're going to run later, you do the same thing as before, where you increment all the way up to 104, print, and then I is 105 in ASCII, so we could just increment 1 more and then print that. So now that we have kind of an idea of how the brainf-ck language works, let's start to write an interpreter for it. So I guess I'll leave this reference up to the side. Most important is these lines over here. So we're going to be using NASM assembly, net-wide assembler, for x86 64 computers, which I assume most people watching will have. So the way to compile a program, let's just show that first, is let's say we have a program, interpreter.nasm. Actually, let's just put some basic stuff in here. Section.text, globals. I'll explain this in a minute. Global start, section.data. So the way to compile a nasm program is using the nasm command line program. And then we're going to do F for format. Format is elf64. And then we put in our file. Oh, wait a minute. I'm in the wrong folder. Okay. Ignore that. What we should be doing, nasm format elf64 interpreter.assembly. And that produces this interpreter.o file, which is an object file. And then in order to get an actual program that we can run, we need to run the linker on it, ld interpreter.o -output interpreter. And then we can finally run it. And then it's not going to be able to do it because we didn't actually write anything in our assembly file yet. So it's just these two commands, the nasm command and the ld command. You don't really need to fully understand it to follow along with this tutorial. You just need to kind of know that just doing these two commands in a row compiles an assembly program. So with that being said, let's start to write our program. So I already typed these 4 lines in. Let me explain what each of them does. Section.text and section.data are the two sections we're going to be working with in our assembly program. The text section is for actual code, and the data section is just for global variables that we're going to be able to access anywhere in the code. So the data is kind of like for storage. Now this global start and this start label, the start label is where the program is going to start, and global start makes it so that the linker is able to see the start label, because the linker will be able to see the start label, but none of the other labels that we define in our code, which is okay. So before we start writing our program, let's first get the global variables that we're going to need out of the way. So the first one we're going to put in is the memory strip, which is a bunch of 1-byte cells in a row. So the way to declare a 1-byte value is db, and then the value you want to initialize it to. So in our case, 0. For our memory strip, though, we want to have 30,000 bytes, which is usually the standard for compiling brainfuck, but it could be anything. So we want to have 30,000 of these 0 bytes. So the way to do that in nasm is times 30,000 db0. Another thing is we want to be able to keep track of where this is and have like a reference to it. So the way we do this is putting a label here. So memory strip. And then this means that memory strip refers to the point in memory where this begins. Actually, let me call it memory start, because then afterwards we're going to put another label for memory end. And memory end refers to the byte right after this finishes. Another thing we need is we need a global variable for our actual code. So we're going to do code start and code end. In this case, we want to actually type something in instead of just having a bunch of zeros. So the way to do this is the db command again, and we're just going to type in a string. So I guess the first program that we'll be interpreting will be printing a new line. Okay, so we've got our 2 most important global variables out of the way. Now we can actually start writing our code. So in our code, the 4 registers we're going to be using in assembly are the the RAX register, the RBX register, the RCX register, and the RDX register. These are each 64-bit registers, which take up 8 bytes. There's nothing really important about them other than the fact that they're just registers that we can freely use. Another register we're going to be using is the AL register, which is actually just the lowest 8 bytes in RAX. So if we want to do operations on 64-bit, AL is the lowest 8 bits, sorry. If we want to do operations on 64-bit values, then we're going to be using RAX, RBX, RCX, and RDX. And if we want to be doing operations on 8-bit or 1-byte values, then we're going to be using the AL register. So let me just put that at the top. Our registers, AL, RAX, RBX, RCX, and RDX. And AL is the lowest byte of RAX. In our program, we're going to be using RCX to point to our current location in the code. And we're going to use RBX to point to our current location in the memory. And RAX and RDX we're going to just use for general purpose registers. So think of RCX as being like the program counter and RBX being the current memory value or the current memory location. So first of all, in our code, we need to initialize RBX and RCX. So we're going to use the move instruction for this. So move RBX code start. RCX should start as code start. So this moves the value code start, which points to the location at the beginning of the code, into the RCX register. And we're going to do the same for RBX, where we move RBX memory start. So now RCX is initialized to the start of the code, and RBX is initialized to the start of the memory. So now we're going to make some kind of loop, because we need to do something over and over again, which is we need to read a value from the code and then execute it. So let's define a label that we're going to be using for that. So exec loop. So the first thing we need to do in our loop is we need to actually read the memory value that we're at. So the way we do this is with the move command again. Move AL. Notice that we're only reading a single byte from the code, so we're going to be using the AL register. Into AL, we move the memory location pointed to by RCX. So this bracket means that we're using RCX as like a pointer, not as actual getting the RCX value. So now that we've done this, we've got AL as our current value in the code. Now we can see what value AL actually has and execute that brainf-ck instruction. So in order to do this, we're going to be using the compare instruction, CMP. So this allows you to compare a register value with either another register value or some constant. So in our case, we're going to be comparing AL with, first let's do the plus sign. And now we can check if it's equal to the plus sign. And if it is equal, then we can jump to a certain location. So let's set a label for where we're going to jump if our current instruction is plus. Just call this label plus. So compare AL with plus, and if it's equal, then we jump to the plus label. Now we can repeat this code except for all of the different instructions. So if it's minus, then we jump to the minus. If it's period, we can jump to the period. If it's comma, we can jump to the comma. And then we can do the same for open bracket, close bracket, left angle, I guess I'll call it, and right angle. And if none of these cases are met, then we know we're at a comment, so we can just increment the program counter using the increment instruction. So inc rcx, and go back to the loop using the jump instruction, which will just, it's basically a go-to. So let's make all the labels that we mentioned here, but we never actually defined. So we're going to have the plus label, minus label, period label, comma label, open bracket label, close bracket label, left angle, and right angle. So let's just go through each of these cases and see what we're going to have to do. So the easiest case to do is going to be the plus label. So if we encounter a plus sign in the code, what we have to do is we have to read our current memory cell value from RBX, increment it, and then put it back into this memory start list over here. So first of all, we need to load our current memory value into the AL register from RAM. So to do that, we're going to use the move instruction. So move AL RBX, and then increment AL, and then we're going to put it back into RBX. So move RBX AL. Note that the first argument in the move instruction is what we're moving into, and the second argument is where we're moving it from. So then once we've done that, once we've incremented, then we can just jump back into the loop. So to do that, we're going to increment RCX, which is our program counter, and jump exec loop. So the code for minus should be very similar. I'm just going to copy paste minus. So the only difference is that instead of incrementing, we're going to decrement. Okay, so that's good. The next easiest case to do will be the two angle brackets. So let's take care of those. So the angle bracket switches our current memory cell location, one to the left or one to the right. So in order to do this, in the case of the right angle bracket, we're going to move it one to the right. So we're going to increment RBX. The one thing is that memory should loop around the edges. So if you try to move to the right and you're at the end of it, then you should move all the way to the beginning. And if you try to move to the left from the beginning, you should move all the way to the end. So we're going to use comparison to do this. So I guess this is the easiest way to show it. Yeah, okay. Compare RBX with memory end. So if we were already past the end of the memory, then jump if equal to right angle loop around. And then in this case, we're going to move a new value into RBX. We're going to move the memory start. So in either case, once we're done with this, then we need to increment the program counter and jump back to the loop. So that is easy enough. We can just copy paste that. Now for the left angle bracket, we should have a very similar code, except instead of incrementing over here, we should be decrementing, and this check should be done a little bit differently. So first we decrement RBX. Then we compare it to memory start in this case, because if it's less than memory start, we want to loop around to the end. So memory start. In this case, we want to jump if it's less than memory start. Note in this previous case, we jumped if it's equal to memory end, because memory end points to the memory location directly after the end of the list, rather than like the last one in the list. Whereas memory start points to the first one in the list, not like anything beforehand. So jump if less than to right left angle loop around. And if we don't loop around, then we just increment RCX and jump back to the loop. But if we do want to loop around, then we need to set a label for that. We move a new value into RBX, and new value we're going to move in is memory end -1, because memory end points to directly after the end of our memory strip. And then we increment RCX and loop around. The next case we're going to take care of is periods and commas. To do this, we need to print our current value to standard input and standard output. And in order to do this, we need to do Linux system calls. So if you're not using Linux, this should be fairly easy to adapt to whatever operating system you're using. In the case of Linux, we're going to be using the write system call to print out for period, and the read system call to read in a value for comma. So in order to do this, we need to set up our registers with the correct values. For the case of the write system call, the RAX register needs to be 4, which is just the number of the write system call. And RBX is the file descriptor for what we want to write to. In this case, our file descriptor is we want to write to standard out. And then RCX and RDX need to be the message that we want to print and the length of the message. Specifically, RCX needs to be a pointer to the message. So we're going to just make this be a global variable, because that's just the easiest way to do it. So single character message. And we're just going to have a single byte initialized to 0. So before we print, we want to actually, you know what I can do instead? I can just, instead of making a new byte that we print from, we can instead just print directly from our memory data thing. So let's do that. So move RCX. RBX points to our current value in memory. And our DX should be the number of bytes that we want to print. In this case, we just want to print a single byte. Now, before we do any of this, oh, actually, let me just put the final line of doing the syscall. So int 0x80 calls the 80 interrupt, which is what you need to call in order to do any system call in Linux. Before we do this, we should preserve the values in RCX and RBX so that they don't get lost while we're overriding them. So the way we're going to do this is using the stack. So we're going to push RCX, push RBX, and then afterwards we can pop them off the stack. So pop RBX, pop RCX in reverse order because of the way stack works, first in, first out. Last in, first out. So once we do the syscall, we've printed that single character to standard out. Then we can do the same thing we've always been doing, incrementing the program counter and jumping back to the loop. Now for comma, we're going to be doing the read system call. So this is system call number 3. So move our AX3. RBX needs to be the file descriptor for what we're reading from. In this case, we want to do standard input. So move RBX 0 means standard input. And same as before, RCX needs to be where we want to read into, and it should be a pointer. And RDX should be the number of bytes we want to read. So this is actually going to be the exact same as before. So we could just copy paste this. So RCX should be location to read into, and RDX is the number of bytes to read. And then after that, we can call the interrupt 80. And we should be doing the same thing as before, where we push and pop our values to preserve them. So push RCX, push RBX, and then afterwards, pop RBX, pop RCX. Then we increment our program counter and jump back to the loop. Now brackets are going to be a little bit more annoying to deal with. The reason for this is because when you get to a closing bracket, you need to find the corresponding open bracket to jump to. And this can get complicated in the case of nested brackets, nested while loops. The way we're going to do this is, let's say we have like code plus bracket, bracket, plus, 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 close bracket, close bracket. So each time when we're running our program, we encounter an open bracket, we're just going to push its location onto the stack. So when we're running this code, we push this location, then we push this location. So the second bracket is going to be on top of the stack. And then when we get to a closing bracket, we pop from the stack to get the location of the most recent opening bracket that corresponds to it. So in the case of open bracket, this is actually very easy. Push RBX, and then increment a program counter, and jump back to the loop. In the case of a closing bracket, we pop into, well, there's two cases for a closing bracket, right? Because it's a while loop. So we want to jump back to the corresponding open bracket if our value in the memory is non-zero. And if it's 0, then we just continue on in the program. Yeah. So first we need to get our value in memory. So move AL RBX with brackets around it. Then we want to compare it to 0. If it's equal to 0, then we're going to do close bracket 0 case. And then otherwise, in the case of non-zero, what are we going to do? We're going to be looping around to the corresponding open bracket. So that's easy enough. We just pop into RCX and then loop around. In the case of a 0, we want to pop from the stack, but we don't want to actually use that value. So we're just going to put it into RAX and then just ignore it. Then we increment our program counter and jump back to the beginning of the loop. Okay, that should be it. This interpreter should work correctly. Oh, one case I forgot to take care of. What happens if you get to the end of a program? Because right now that case is not dealt with. Our assembly code should exit out once you get to the end of the program. So this is easy enough to do. Right in the beginning of exec loop, we can do compare our program counter RCX with code end. And if it's equal, then we jump to exit. And now we just need to make an exit function. So in order to exit out an assembly, you need to do a syscall. The syscall number is 1, and 1 exit syscall. And then the one other argument you need to give is the exit code. Usually how exit codes work is you want to have an exit code of 0 if your program ran successfully, and 1 if it ran unsuccessfully. So we're just going to put a 0, assuming that we ran successfully. And finally, we call the interrupt. So we should be done now. Let's see if this works. So first we're going to call nasm format elf64 on interpreter.assembly. Then we're going to call ld for the linker, interpreter.o for the object file, and then we want to output to interpreter. Now we should be able to run it. And it does exactly what we expected. It prints a single new line because our code increments the value 10 times, prints, and the ASCII value 10 is a new line. So let's get some more complicated programs and see if they can run. Let's just jump ahead to this. Let's jump ahead to this one actually. Input a character and print it until a new line is inputted. So we can compile this and link it and then run it. So we're going to input some characters like A, B, C, D. Oh, what just happened? So we seem to not be inputting characters correctly. Let's see why that is. Let's try just input a character and print it. So we're going to compile and link and then run. We input the A character and it prints it back at us. So we need to figure out why it's exiting out early. And I think it has to do with our closing brace. So let's see. In the case of opening bracket, we push. Oh, that's why. Okay. In the case of the opening bracket, we should be pushing our program counter, but we're actually pushing our data location. So this is easy enough to fix. And let's try the same program again and hope that it works. So we compile, link, and run. So we should be able to type some text and have it say the text back at us. So A, B, C, D, E, F, enter, and it says it back at us. Now, just for fun, let's try to have it increment all of the characters we put in before printing back at us. So we just add one more plus sign and compile and link and run. So A, B, C, D, E, F. This should print out B, C, D, E, F, G. And that's what it does. Good. Let's see some more of our sample programs to run. What's it called? Let's have it try to print hi at us. We're going to compile or assemble, link, and run, and it prints hi. Good. Now there is one more case we need to deal with before we can call our interpreter finished. In that case, if you look on the screen on the right, is this loop over here. So what this should do is, since it's a while loop, not a do while loop, it should first come to this opening bracket, see that the current memory value is 0, and then just skip the loop entirely and terminate the program. But what it actually does, if you compile it and run it, is it prints all of the characters from 0 all the way up to 255, and then exits once it reaches all the way back down to 0 again. So what we need to do is we need to make an extra case in open bracket that checks if the current memory value is equal to 0. So this is going to be done differently than the way we did before with finding the corresponding open bracket for the close bracket 0 case. And the way we're going to do this is, let me show you on the screen on the left. So let's say we're trying to do this code. And we reach this opening bracket. We want to find the corresponding close bracket. What we can do is we can have a counter. The counter starts at 1. It's incremented every time it reaches an opening bracket, and is decremented every time it reaches a closing bracket. And once the counter gets to 0, we know we found the corresponding close bracket to our opening bracket. So let's just start coding this up. In opening bracket, first, before we do anything, we need to make a comparison. So compare, first we need to read the memory value. So move AL RBX. We need to compare AL to 0. If it's equal to 0, we will make a separate case for that. Open bracket 0 case. Otherwise, we do the same thing we did before. So for the 0 case, we're going to store our counter in RDX. This is the first time we're using RDX, but we just need a register to use, so you might as well. Our counter gets initialized to 1. And we start right after the opening bracket that we started at. So that means that we just need to increment our CX. So now we're going to loop around. We're going to repeat looking at the current character until this RDX turns into 0. So open bracket loop. So first we need to, in the loop, we need to read the current code location. So move AL RCX. If the code location is opening bracket, we need to do one thing. If it's a closing bracket, we need to do another thing. Otherwise, we just continue on in the loop. So the way we code that up is compare AL with opening bracket. If it's equal, then jump to open bracket case 1, let's call it. Then compare it to closing bracket. And then this will be open bracket case 2. Otherwise, we can just increment the program counter and jump to the loop again. Oh, one thing we should do before we do any of this is that we should also check if we're at the end of the program, and if we are, we should just exit out. So the way we do that is compare RCX with code end, jump of equal to exit. Okay, so now we just need to make these two cases. So open bracket case 1. We see an open bracket in the code, so we increment RDX, increment our program counter, and jump back to the loop. Case 2, we first decrement RDX. In the case that we have reached the closing bracket, we want to increment our program counter one more and then jump back into our normal code loop that we've been writing this whole time. Otherwise, we continue doing this open bracket loop. So let's do that. I guess first what we should do is increment our program counter. Now we compare RDX with 0. If it's equal to 0, then we can go back to the normal loop, exec loop. Otherwise, we jump back to open bracket loop. Now I believe this should work, so let's run it and see what happens. And good, this does exactly what we want to. And just to be sure, let's see if cases where we actually shouldn't skip this, let's see if those cases still work. Good, that does what we expect. So now we've completely finished off our interpreter. Just for fun, let's run one more program, which is a very complicated brainfuck program that prints out the Mandelbrot set. It's 145 lines long. So we're just going to copy this directly into our interpreter in this code section over here. And then we need to bring it all into one line. It's going to take a bit. Oh, there we go. Join that together. I think that worked. Let's compile it and see what happens. Good. So we're printing out the Mandelbrot set. This is a brainfuck program doing it, not any code we've written. So yeah, we've completely finished our brainfuck interpreter. The code will be posted in the description of the video. And thanks for watching.